Let's start this lecture now. First of all, disclaimer, AP is a trademark registered by the College Board, which is not affiliated with and does not endorse this resource, nor is the 5.5 team. As usual about 5.5, this review session was prepared by reading as part of 5.5. Led by Lance, 5.5 is a volunteer serial initiative with more than 70 volunteers and more than 10,000 combined volunteer hours that seeks to provide resources for students taking AP courses. Consider checking out our website, 5.5.org, for additional AP resources and practice exams. If you'd like to contribute to 5.5 by creating resources, hosting lectures, or promoting this project, please check out the application document for more information. Applications will be reviewed on a rolling basis. Here are some expectations. You can ask any question at any time. You're encouraged to participate in activities using chat, because you reinforce your understanding. Please use spoiler tag for answers. Finally, please fill out the 5.5 lecture feedback form at the end of the session. Or if you cannot stay till the end of the session, you can fill it out before you leave. That will help me improve my lecturing skills. Without further ado, let's take a look at our table of contents. As usual, we have sequence and series. We'll look at definition, tests, and also some alternating series. Then we'll take a look at power series, which include Taylor-Maclaurin, Lagrange error bound, and their properties, which include the integral of convergence. And then we'll give a list of additional resources for you to use later. And then we'll have question and answer at the end. First of all, let's take a look at divergence versus convergence, which is the first topic of this unit. First of all, infinite series is an expression of this form. We have a equals to 1 till infinity. You might also have a equal to 0 sometimes. For each positive integer k, the sum sk, where the upper bound changes into a positive integer k instead of infinity, this is called the k's partial sum of the infinite series. The partial sums form a sequence of sk. If the sequence of partial sums converges to real number s, the infinite series converges. If we can describe the convergence of series to s, we call s the sum of the series, and we write this expression. However, if the sequence of partial sums diverges, the series diverges. That is the definition of an infinite series. And then we have our geometric series. It is a series of this form, where we have ar to the power n minus 1, from n equals to 1 to infinity. So if we expand it, we have a plus ar squared plus ar3 to the power 3 plus ar to the power 4, and so on, till infinity. To know whether the series converges or diverges, we need to take a look at the ratio. Geometric series have a common ratio. So if the common ratio is bigger than -1 and smaller than 1, which means that the absolute value of it is smaller than 1, the series converges, and we have a formula to calculate its sum, which is a over 1 minus r. Do note this sum only exists for if the series converges, so for the absolute value of r smaller than 1. If the absolute value of r is bigger or equal to 1, the series diverges. When the series diverges, it does not have a sum. I have a question in the chat. On a big picture, how does it look on a graph like divergence and convergence means? Usually for divergence, the graph will look like something like this. So it somewhat has a horizontal asymptote. It can be a bit deceptive to look on the graph, because it might look like this, but it might be still divergent. But this is for convergent series. For more obvious divergent series, you might see the sum going up like this, so it is obviously approaching infinity. So basically, for a series that converges, this graph will look like it has a horizontal asymptote, and it is approaching a certain value, so which is a sum. If it diverges, then it will increase indefinitely. Let's look at tests to actually test whether a series is convergent or divergent. The first test is called the divergence test, the nth term test for divergence, because it can only prove divergence. So if the limit of the sequence as n to the power of infinity equals to c, and c is a real number, but it does not equal to 0, or if the limit does not exist, then the series diverges. Intuitively, this does make sense, because if your term does not approach 0, then you have an infinite summation of non-zero terms, so it is obviously divergent. This is probably the easiest test to carry out. So if you suspect that a series might be divergent, I would try this out first. But do you know that this can only prove divergence, not convergence? Next, we have our integral test. Let's say our series with positive terms a, n. If there exists a function f and a positive integer n, such that the following three conditions are satisfied: f is continuous, f is decreasing, and fn equals to an for all integers. So the function somewhat models the series. Then the sum of the series, so the series and the integral, they either both converge or both diverge. Question in the chat: how often does the nth term test work on the AP exam since it's so easy? AP course and exam description, so it is possible that it will appear. But whether it will appear, I'm not sure, because I don't know the AP test. But since it's so easy, we should just check it quickly if you suspect that series is divergent. It only proves divergence. As you can see, the integral test is more complex to do, so I will leave it at the end. I will talk about the strategy to select the test later. But here is the integral test, if you want to use it. Make sure the three conditions are all satisfied. And then the series and the integral, which is an improper integral, and you should know how to deal with improper integrals before. They either both converge or both diverge. Let's move on to harmonic series. This is a common series. and it diverges very slowly. So on the graph, it might look like this, but it is actually diverging, so it is increasing very slowly. So it's sometimes deceptive to just look at the graph and say that it converges, but it actually diverges. Our p-series, the harmonic series is part of the p-series. For any real number p, the series 1 over n to the power p is called a p-series. We have a convergence test for that. It converges if p is bigger than 1 and diverges if p is bigger than 0 but smaller or equal to 1. Intuitively, if p is a big number, then the p-series will converge quickly. Suppose that p equals to 3, then I'm going to have 1 over 1, 1 over 8, which is already small, getting small. And then I have 1 over 27, and so on. So as you can see, the denominator is increasing very quickly if p is bigger than 1. When p equals to 1, we have our harmonic series, which diverges very slowly. When p is bigger than 0 but smaller than 1, the denominator is going to have some interesting behavior that make it diverge. So intuitively, we want to make the p bigger if you want to make it converge. So that is the convergence test for p-series. We also have our direct comparison test and the limit comparison test. But let's look at the direct comparison test first. This is more commonly used if you see that the series looks like a geometric series, or look like a p-series, or may look like any other special series, but it is just not directly that. Then we can use our direct comparison tests. Suppose that there exists an integer n such that an is bigger or equal to 0, but smaller or equal to bn for all n bigger or equal to capital Fn. If the series bn converges, then the series an also converges. This intuitively is obviously true, because we know that bn is bigger or equal to an for every term. So if the bigger series converges, the smaller series should also converge. Similarly, we also have another test. So if the smaller series diverges, then the bigger series should also diverge. Because an is bigger than bn for all terms. Yes, direct comparison is sometimes easy to carry out. But let's look at the limit comparison too. This is a bit more complex because we have limits now. So we have two sequences, a and bn. If the limit an over bn equals to a real number l, and it is not equal to 0, then the two series both converge or both diverge. If the limit a over bn equals to 0, and bn diverges, so denominator diverges. Sorry, the denominator converges, then the numerator also converges. If a over bn is infinity, and bn diverges, so if the denominator diverges, then the numerator also diverges. This is the limit comparison test, if your direct comparison test fails. Since it's more complex to carry out limit comparison tests, I will try the direct comparison test first, and then do this. So as stated before, the comparison tests are usually used if you see that the series looks like a geometric series or p-series, but just with some small modifications that makes it impossible to just apply the convergence or divergence test for geometric series and p-series directly. Then we'll use the comparison tests. Finally, we have our alternating series. Any series whose terms alternate between positive and negative values is called an alternating series, which might be in the two forms, where the sign alternates from positive to negative to positive to negative to positive to negative, and so on. So this is a special trick to make the signs alternate. And we can make Bn positive. So we'll make sure that we can have an alternating series. We have our alternating series test. But first of all, let's take a look at the alternating harmonic series. We know that our harmonic series is 1 over n. So our alternating harmonic series will be -1 to the power of n, and then 1 over n. This does converge. We can explain using the alternating series test. An alternating series converges if both conditions are satisfied. First of all, we must have Bn is bigger or equal to Bn plus 1. This intuitively should be true because you want the terms to be decreasing, not increasing. So you want the term to be at least decreasing, and then the limit must be 0. So we want the sequence to approach 0 at the end. So we'll converge to a specific n instead of diverging. This is a useful test if you see an alternating series. And then we'll take a look at the ratio test. Let's say the ratio equals to an plus 1 over an. You can put an absolute value sign, and n approaches infinity. If the ratio is bigger or equal to 0 and smaller than 1, then it converges absolutely. We'll take a look at the absolute convergence later. If p bigger than 1 or p equals to infinity, then the series diverges, because that means that the ratio is going to be bigger than 1 or infinity, so that your terms are actually somewhat increasing, which you don't want. So that means that it diverges. If p equals to 1, the test is inconclusive and it does not provide any information, so you may want to pick another test, such as the integral test or some comparison tests. The ratio test is actually quite useful later when we are trying to get the interval of convergence from power series. But it might also be useful just to test the convergence of series. Finally, we have our absolute or conditional convergence. A series is absolutely convergent if the absolute value for it converges. A series exhibits conditional convergence if the series itself converges, but its positive series diverges. A good example would be the alternating harmonic series, because the alternating harmonic series does converge, but its absolute value series, which is a harmonic series, diverges. So the alternating harmonic series has conditional convergence. We have this relationship, which is also intuitive. If the absolute value series converges, then itself should also converge. Because if you take the absolute value, your sums will add up directly, where if you just have itself, if you have alternating signs, they will cancel each other out. So we'll expect that it will be somewhat smaller intuitively. I've seen a lot of tests, so I think it's helpful to look at how to choose the test. This is not in the course exam description, but I think it will be useful. So we have a series and want to choose a test. The first question we ask is it a familiar series? Is it a harmonic series or alternating harmonic series? Is it a p-series or geometric series? If it is, then can you just check the power p, the ratio r, or I already know the convergent divergence of harmonic and alternating harmonic series, and can use their convergent test directly. The second question is it an alternating series? And are we interested in absolute value, absolute convergence, or just convergence? If we're just interested in whether series convergence, then we will apply the alternating series test, which is suitable for alternating series. If we want absolute convergence, then we just skip to step 3 and consider the series of absolute values. Then, is the series similar to a p-series or geometric series? If it is similar, but we cannot just do step 1, then we'll try some comparison test. And if the direct comparison test fails, then I'll try the more advanced limit comparison test. Otherwise, do the terms in the series contain a factorial power? If so, try the ratio test first. So if it contains a factorial power, it will be easier for me to use the ratio test and get a conclusive result. And it is easier to determine the ratio. All those fails, then we will use the divergence test. We have the nth term divergence test. Not provide any information, so we can finally try the integral test, which is a lot more difficult to do. So we will leave it at the end. Now we can choose a test, so we can save our time by have a strategy. Let's take a look at an MCQ. Which of the following series is conditionally convergent? So as we can see, where there are alternating series, we want series that are conditionally convergent. Feel free to take your time doing it, and I'm going to create a poll in chat, so you can pick your answers after that done. For those who just joined, we are doing an MCQ problem right now using the tests. Just in case you didn't see the slideshow over this in it. Slide 19. If you're done, please send your answer in the poll in the chat. And after most people are done, I will go over the answer. Interesting. I saw an approximately an even split between choice A and B in the poll. I will go over this question in 1 minute. So feel free to choose your answer before that. You don't have time to apply the tests in full. You can try to use your intuition to kind of guess which series is conditionally covered. Let's take a look. So we are given 4 alternating series, and you want to see which one is conditionally convergent. Let's take a look in order. So for A, my first glance said it looks like a P series because I saw k power 3. But this is also not really a P series. So here, it is directly not a familiar series, but it's similar to P series. So I will try the comparison test first. Because we're asking for conditionally convergent, not absolutely convergent, so I will try the absolute convergence first because it looks like they will satisfy the absolute convergence. So for absolute convergence, I will ignore this temporarily to see whether it's absolutely convergent. This is very similar to 5 over k to the power 3. And we know that this one is smaller because it has a bigger denominator. So if you have this relationship, we can use our direct comparison test. And if you forgot that, it is the first one. So right now, we know that Bn converges because this is a P series and 3 is bigger than 1, so it does converge. If the bigger series converges, then the smaller series must also converge. So the choice A has absolute convergence instead of conditionally convergence. So we cannot choose choice A, unfortunately. Let's take a look at choice B. So choice B is an alternating series and it's 5 over k plus 1. So it loses the power of 3 here. Otherwise, it is very similar. So we also want to do a comparison test because this is so similar to P series, 5 over k. I'm going to take a look at absolute convergence first. So let's try to use a direct comparison test first, and if that fails, I can use other tests. So the similarity is 5 over k, which diverges. The problem is that the relationship is that 5 over k is bigger than 5 over k plus 1. So that means that it doesn't really satisfy second one. So we cannot use the direct comparison test. We have another choice though. We have our limit comparison test. So I can use n over bn and try to get what the limit is, and then I'll choose which one to use out of the three. So let's say we have, 5 over k over 5 over k plus 1. It's a complex fraction, but I can simplify it and cancel all the 5s, and I'll have k plus 1 over k. The limit is 1 as k approaches infinity, so it is a real number that is not 0. That means that I can use the first one because the limit is 1, not 0. So they both converge or both diverge. I already know that one of the series diverges, so the other series must also diverge. So that means that the absolute value series is divergent. Then I will apply the alternating series test, which tests whether the series itself is convergent. Before looking at that, I have a question in the chat. Why can't we use direct comparison for B? So the main problem is the series we are familiar with is 5 over k. It diverges. So from the comparison that we're trying to prove that the absolute value series diverges without the alternating. So from our direct comparison test, it requires the series that we're familiar with, which is Bn, is used as a condition here. We know that Bn diverges, so Bn in this case is 5 over k. And our familiar 5 over k is the familiar series. But we are trying to prove that 5 over k plus 1 diverges. Unfortunately, the sign is contradicting each other because the denominator is plus 1. So it is definitely smaller than 5 over k. This means that we cannot use the direct comparison test immediately. Still, we can use our limit comparison test to get that it actually diverges. Let's use the alternating series test, which requires this to decrease. It obviously does when the denominator increases. And it requires that the limit as k approaches infinity, the limit is 0. It is because if k approaches infinity, the denominator is going to be infinity, so it is 0. So this is conditionally convergent. We can see that's B now, but let's take a look at C and D too. For C, we have 5k over k plus 1. This doesn't look right because I can see the limit is 5 now, as k approaches infinity. The limit is 5. So it is not convergent. The series itself is not convergent. So it's definitely not conditionally convergent. For D, it's even crazier because I have k to the power 2. So the limit is infinity. It clearly diverges. So the correct answer is B. So the confusion is between choice A and B. The main problem is that A is absolutely convergent instead of conditionally convergent, so we cannot pick that. And feel free to ask any questions. Otherwise, I'm going to move on to the next topic. Okay, let's take a look at the alternating series error band. So we want to get the possible error or remainder of our approximation using an alternating series. So we want to see that if we pick the first n terms, how close will my approximation be? This is useful in real life applications because we want to do less work because we cannot do too many terms. We also want a reasonable error. So this is a very useful error bound. So we have an alternating series that satisfies the hypotheses of the alternating series test. So it must be convergent first of all. Otherwise we will not have a sum anyways. And S denotes the sum of the series, and Sn denotes the nth partial sum, which is the sum of the first n terms. For any integer n bigger or equal to 1, the remainder, which is the error, satisfies this inequality. So the absolute value of the error must be smaller or equal to the next term, be n plus 1. This is a simple error bound compared to Lagrange error bound. So sometimes, if your Taylor or Maclaurin series is an alternating series by chance, then I would choose this error bound other than applying the Lagrange error bound because that is too long to do. So this one is simple. The error is the next term. So it is intuitively true because for an alternate series that converges, you're going to jump between places. So imagine a number line. I'll jump here, and then a bit back, and a bit forward, a bit back, and so on. So it will slowly converge to a single point somewhere here. So the approximation is getting more and more exact, and the error should be less than the next term. So this is the alternate series error bound. That let's take a look at, finally, Taylor-Maclaurin series. If f has derivatives of all orders at x equal to a, so you can infinitely do differentiation. So it has second derivative, third derivative, fourth derivative, and so on. Then the Taylor series for the function f at a is this series. The general term is the nth derivative of f(x) at a over n factorial times x minus a to the power of n from a equals 0 to infinity. So it looks like fa plus the derivative of fa times x minus a plus the second derivative of fx at x equal to a over 2 factorial times x minus a squared, and so on. It's quite complex. So we have a Maclaurin series if a equal to 0. This is the basic definition. And then if a function f has a power series at a that converges to f on some open interval containing a, then that power series is the Taylor series for f at a. This is kind of the uniqueness of power series. And as usual, we can just pick the first n terms and do somewhat an approximation. As usual in real applications, just like the alternate series, we don't have the power to brute force so many terms. So we want to keep the error low, but we don't want to do too much work. So that is the Lagrange error bound later. So we have the nth Taylor polynomial, which is the first n terms. Actually, it might be n plus 1 terms because we have fa. So If the nth Taylor polynomial for f at 0, so a equal to 0, then we have the nth Maclaurin polynomial instead. Yes, that is accurate. So a Taylor series is a specific type of power series, and a Maclaurin series is a Taylor series centered at 0. I guess we have some special names. Let's take a look at our first exam FRQ, which as usual number 6. So as you can see, we have a graph and a tangent line, and we have a table of values. A function f has derivatives of all orders for all real numbers x. A portion of the graph of f is shown above, along with a line tangent to the graph of f at x equals to 0. So this is a tangent line. Select the derivatives of f at x equal to 0 are given in the table above. So the second derivative of f at 0 is 3. The third derivative of f at 0 is negative 23 over 2. Interesting number. But the fourth derivative of f at 0 is 54. Part A tells us to write the third degree Taylor polynomial for f about x equal to 0, which is the third degree Maclaurin polynomial for f. So we have a question in chat. Third degree meaning, does it mean that we stop when we get x power 3? Yes. So it's based on the degree. Your time and type your answer in the chat after you get it. The expression unfortunately is going to be a bit long. And please use smaller text likely, so other people can see your answer directly without clicking it. I'll be happy to see your answers in the chat. We have a question in the chat. Do we need to simplify factorials? You do not need to simplify. For the AP exam, you do not need to simplify. But if your teacher wants you to simplify, so they can mark the paper faster, they might need to do so. But on the AP exam, no. And I've seen some very good answers in the chat. Let's take a look. So for the Taylor polynomial with x equals 0, I would just look at the definition first. So I will stop when the power reaches 3. So I'll have 4 terms. So we have f0 because it is at 0. So I will take a look on the graph, see what f0 is. It looks like 3 to me. And I want the derivatives up to 3. I don't know what the first derivative is, but we're given a tangent line. We know the slope of the tangent line is the derivative. So I can pick 2 points. Let's say I pick those 2 points, and I do rise over rho. So I believe you all can do rise over rho now. So the slope is -2. I can add another entry to the table. So we have 3 minus 2x. I'm just going to show this. So we determine those through the graph. So we have 3 minus 2x. And then we're given the derivative already here. It is 3. So I have 3 over 2 factorial x squared. And then I will look at the third derivative, which is negative times 3 over 2 on the table. So I put it here over 3 factorial x to the power 3. And if we simplify, we get this answer. And congratulations for getting it correct. 1 point for 2 terms, 1 point for the remaining terms. 1 point and 1 point. And if you have any questions, feel free to ask now. No questions, let's go to the next part. Language error bound. And notice that if your power series, if your Taylor series is an alternating series, then I will use the alternating series error bound first. Because this looks like a nightmare to do. Anyways, let's take a look. Let f be a function can be differentiated n plus 1 times an interval I containing real number a. Pn is the nth Taylor polynomial of f at a, and this is the nth remainder. if there exists a real number m such that the n plus 1 derivative of f at x is the absolute value of it is more or equal to m. So m is the biggest possible. Then we'll have this error bound. Plus 1 factorial, and the absolute value of x minus a to the power of n plus 1. This actually looks like the next term. So it's somewhat similar. This is also somewhat the next term. We have n plus 1 derivative over n plus 1 factorial, and x minus a also to the power n plus 1. So similarly as the alternate series error bound, it is also somewhat the next term. And this is called the Lagrange error bound. However, puts a definition of power series later. So the series of this form is a power series centered at x equal to 0. So we have x to the power of n, and we have a constant in front. As you can see now, Taylor series and Maclaurin series are actually two special types of power series. Because it looks like this. We have a coefficient in front, which is fn a over n factorial. That is the coefficient. And we have x minus a to the power of n as we go. So this is a power series. Where the center at is important later to determine the radius convergence and interval convergence. So we need to take a look at this specifically. So if we see x minus a to the power 2, and then so on, then I would say that it is centered at x equals to a. And let's go to see the convergence of power series. For any power series, it satisfies exactly one of these three. So whether it converges at the center and diverges for every other. So in this case, it only converges at x equal to a, because the whole series is going to be 0 if you substitute that in. And it diverges for every other number. The second case is that it converges for all real numbers x. And the third case is that there exists a real number r bigger than 0, the radius convergence, such a series converges if the absolute value of x minus a is smaller than r, and diverges if it is bigger than r. As the values x where it equals to radius convergence, the series may converge or diverge. Generally, there will be a special case there, so it might be someone like a harmonic or alternate harmonic or some other normal series, usually. So we can determine that. So remember that for the third case, it converges within the strict inequality within R, and diverges if it is strict inequality bigger than R, and at the endpoints, we need to determine that ourselves. For power series, the set of real numbers x where the series converges is called the interval of convergence. So it is the interval numbers that the power series converges. If there exists a real number r bigger than 0, such that the series converges just like this, which is the third case that we have just talked about. Then r the radius of convergence. So there's a difference between interval and radius. If the series converges only at the center, then the radius convergence is 0. If it converges for all real numbers, the radius is infinity. We generally use the ratio test because we have a power here. And we sometimes have factorials for the Taylor and Maclaurin theories. So when we look at the picture about how to choose a test, we can see that if it contains factorials or powers, we'll prefer the ratio test. We can differentiate and integrate a power series. We do it term by term to differentiate each term. So let's say that power series converges on the interval. Then f is a function defined by a series, usual power series. Then f is differentiable on the interval and can find the derivative by differentiating the series term by term. So let's look at general term. To differentiate this, I believe we can all do differentiation now. So we put the exponent in front and subtract the exponent by 1. So we have this result for a general term. So it's a term by term differentiation. We can also integrate it term by term. So I divide it by n plus 1 and then I increase the power by 1. The definition for term by term differentiation and integration. There are a couple of interesting points here. No question in chat. For Taylor series, would that just mean shifting it forward by one derivative? That's actually a pretty interesting question because I have never thought of that before. Yes, so the first term will disappear because it is a constant, and then we'll start off the derivative of f at c. That's an interesting question. Although it shifts forward by one derivative, the coefficients might not stay exactly the same though. Coefficients might change because we have an n here. I will definitely take a look at that later. That's an interesting thought. But let's go on. And I will warn you that the endpoints might change. So if the series is originally convergent at the endpoint, it might be divergent if you differentiate or integrate it. So as usual, please double check your endpoints. but the radius will stay the same. The interval might change because the endpoint might change. So that is one. We have some common Maclaurin series that we should try to memorize so I can save some time. If you forgot, you can do this again by manually doing the work. So for function 1 over 1 minus x, its Maclaurin series is x to the power of n. Very interesting. So, and its interval convergence is from -1 to 1. For e to the power of x, the Maclaurin series is x to the power of n over m factorial. This is because the derivative of e to the power of x is itself. So the coefficient will always be 1 over n factorial because e to the power of 0 is 1, which is not shown here. And it's Maclaurin series, so it centers at 0. So we should use the derivatives at 0. For sine x and cosine x, we have this. So the meaning that it is skipping some terms is because that sine 0 is 0. So it somewhat eliminates some terms. And the derivative is kind of alternate towards sine and cosine because we know that the derivative of sine is cosine and the derivative of cosine is negative sine. So it has some interesting behavior. If you got it, not a big deal. You can use the definition again. It will form some pattern. And for the last three, its interval of convergence is every real number. And for topic 110.15, it is kind of a combination of things. So we can obtain a power series of function based on another power series. If the function is the derivative of another common function, I will use term-by-term differentiation. And if it's an antiderivative, then integration. If the function is a sum or difference of multiple common functions, I will use addition subtraction. I can use substitutions. So I can change the x to x minus 1, for example, and I substitute it here. Other properties. I believe that we have covered almost everything. So now it's time to do some problems. This is a full exam of RQ. Let's do it part by part, A, B, C, and D. So let's read the question together. The Maclaurin series for a function f is given by n plus 1 x to the power of n over n squared 6 to the power of n, and converted to fx for all x in the interval of convergence. It can be shown that the Maclaurin series for f has a radius of convergence of 6. So the radius of convergence is 6. That is very useful for us if we want to determine the interval convergence later. Okay, determine whether the Maclaurin series for f converges or diverges at x equal to 6. Give a reason for your answer. Let's do part A right now, and I will have to see your reasoning in the chat. If you just joined, feel free to do part 8 right now. And message your answer in the chat using the support text. Okay, let's take a look. And interestingly, for VC tests, the 6 FRQ will almost always be a unit 10 FRQ. So as you can see, the Cauchy number is always this. So let's take a look at part A. We're given the radius convergence, so I want to see whether 6 is in the radius, is in the interval or not. I can see directly from this that the center the interval, the radius of convergence 6. So I can say that at least I know that between -6 and 6 it converges. Unfortunately, x equals 6 is at the endpoint. So I cannot say whether it converges or diverges immediately from the radius. However, I can do a substitution. So substitution worth 1 point. So please, at least do a substitution. And this looks like the harmonic series because I would look at the exponents. So the exponent is 1 or 2. So exponent looks like somewhat -1, which is the harmonic series. So the exponent looks like the harmonic series, so I will try to use the direct comparison test first because it is easier. And we can use that because this series is bigger than the harmonic series for all integers. If you cannot directly see why, I will break it down into 2 fractions and it will become obvious. This is n squared here. So this is obviously bigger than 1 over n. So we can apply the comparison test and it diverges. So the other point is earned if you answer that it diverges with your reasoning, which is a comparison test. Currently, we don't have limit comparison here. Can you use ratio test for this question? Ratio test is not very good here because we don't have a factorial or power of n. If we try to use it, we'll have this thing over n plus 1 squared. So this will be equal to n squared n plus 2 over n plus 1 to the power of 3. This equals to 1, by the way, for the limit. So the ratio test is inconclusive. So we can't really use that, unfortunately. Yes, that is used to prove that our series is bigger than the harmonic series. And by the way, root test is not in the course and exam description, although it is very common. Sometimes, if you want to use root test, you can use it, but you don't have to use it. The root test is not on the curriculum. Yes, I have taken a look before while making the section, and there's an exclusion statement. The nth term test for divergence, the integral test, comparison test, limit comparison test, alternating series test, and ratio test for convergence are assessed. Other methods are not. So the root test is not on the eighth test. Yes, we have something bigger. We know that 1 over n diverges, so the bigger series must also diverge because it is bigger. So the description in the chat is correct. The explanation is nice. If we want to prove divergence, then our series must be bigger than the common series that we know. And Rachel test here gives us 1, which is inconclusive, so we will try another test. Here are some scoring notes. To earn the first point, we must have the term with substitution. You can just simplify it and skip the step. That is also okay. Either individually or as a part of a sum. For the second point, you must demonstrate that the terms n plus 1 over n squared are larger than the terms in a divergent series. So this response, just only this response earns both points, because it considers n plus 1 over n squared, so it satisfies the first point, and you show that it is bigger than 1 over n, and you give the answer that diverges, and you give the reasoning, so this answer is perfectly fine and earns both points. So just those little words. To the chat, if the smaller series diverges, then the bigger series diverges, but the other way around might not be true. One does not need to use the term comparison test, but you cannot declare an incorrect one. So I would not say anything about that. Not declare an incorrect test, but you don't need to. Just like simplification, you do not need to simplify, but you simplify wrong there, you get a deduction. Limit comparison test as well, which is a more advanced version of direct comparison. And you can look at the solution here if you want. Limit equals 1 and the harmonic series diverges, then the series also diverges by limit comparison test. And if you use the limit comparison test, you must write the limit of the ratio terms in a given series to the terms of divergent series, which in this case is 1 over n. That is the easiest divergent series. And demonstrate the limit is 1. As usual, you don't need to declare what test you use, but you cannot declare the wrong one. Yes, if you don't like the direct comparison test, you can use the limit comparison, which is usually contain more possibilities. But the direct comparison test is easier. Sometimes the limit comparison test is also good. That is part A. So 2 points. 1 point for the series with substitution, 1 point for answer with reasoning. Okay, after we are done with part A, let's look at part B. It can be shown that f-3 equals to the substitution, and we can simplify it to this, and that the first 3 terms of this series sum to negative 125 over 144 show that the remainder is smaller than 1 over 50. Very interesting question. Feel free to do the question and briefly explain the reasoning. You don't need to type everything out because this could be a bit tedious. Just show the key points in the chat. They gave me our series, and the first 3 terms is just this. We want to show that it is smaller than 1 over 50. So that should really remind you of some error bounds. It looks like an error bound. We have learned 2 error bounds, and which one to use depending on your preference. I would love to see your answers in the chat. Just joined, we are doing part B. Since part B is kind of a proof question, you can briefly see the reasoning in the chat with borderlines. If you're stuck on the part B, the hint will be we want to prove that the error is below 1 over 50. So it's kind of an error bound. And another thing would be this series. Of course, it is a Maclaurin series. You can also say that it might be an alternating series because we have negative 1 over 2 to the power of n. So you want to use an error bound. If you forgot about the error bound, you can take a look at these slides. The slide is buried in chat, so I'm going to send it again. Yes, you can use alternating error bound. If you want to use Lagrange, feel free to go ahead. Quite similar. I believe alternating would be the best for us. Let's take a look. We have a bit short on time, so I have to go ahead. As I just said, this is an alternating series, so we can use the alternating series error bound. If you remember, to use the alternating series error bound, it must converge first to use it. So the proof of convergence is quick. First of all, you can use the alternating series head because it obviously decreases to a magnitude of 0, and is also within the radius of convergence, or in interval convergence. It is -3. And then we can apply the alternating series error bound, which says that it is the fourth term. The error must be smaller than the fourth term. And apparently, the fourth term is bigger than 1. Apparently, the fourth term, it will give an even smaller result. So let's take a look at the solution. So you can double check that it is an alternating series that decreases in magnitude to 0. It is one of the conditions to apply the tests. This is an alternating series because they have negative something to power of n in here. You can actually separate it to just -1n and then 1/2n by some exponent properties. So it will become clearer that it is alternating. By the alternating series error bounds, approximate with an error of at most the fourth term. So I can do a substitution of n equals to 4 into the series to get 5/256. This is smaller than 1/50, so the error bound is smaller than 1/50. Some scoring notes. So the first point is earned if you use a fourth term, and the second point is earned for verification. So the first point is earned for correctly using x equals to -3 in the fourth term. Listing the fourth term as a part of polynomial is not sufficient. And if you use it in any term of degree 5 or higher, it doesn't earn this point. So if you accidentally use a fifth term, then it will not count. The expression earns the first point, but just the value does not. So please show some work. If you do this and you simplify incorrectly, you earn the first, but not the second. Just the presence of this earns you a point. To earn a second point, you must state that the series for f-3 is alternating, or the alternate series error bound is used. And this response is perfectly fine if you indicate that series is alternating. And if you just say the error is 5 over 256 without comparing, you see the error is equal to. And for the error bound, the error is actually not directly equal to that, though. It is smaller or equal to. So if you say that, unfortunately, it doesn't earn the second point. Because this is error bound, not the error. This is some detailed story now, so very interesting. So in summary, this earns 1 point for using the first term. And if you see the alternate series, this earns 1 point. Or this one can also earn a point. So that's how this works. With part B done, let's take a look at part C. And of course, if you have any questions, you can ask at any time. Find the general term of the Maclaurin series for the derivative of f. Find the radius of convergence of the Maclaurin series for the derivative of f. Talked about it before, about the derivative. So, for you to do this now, I'll give a hint in 2 minutes if you don't know how to do it. Question, if you just say the fourth term equals to 5 over 256, all counts, because just it does not earn the first point. So we'll lose a point if you just did it. I'm going to go back to the question so people can see it. But just the 5 over 256 does not earn the first point. So please find the general term. You have the general term of the original series, so you can do some differentiation, and then find the radius of convergence. Your answer is in the chat. I just need the general term and radius. If you want to type the reasoning, you can, if you want to. I'll give a hint soon if you don't know how to start. By the way, for people who just joined, we are doing part C of this FRQ. And fortunately, part C is not related to any other previous ones. Not really related to part A or B. The hint is that you can use term-by-term differentiation. In other words, you can differentiate the general term. That's the hint for this part C if you don't know how to solve. N as a constant in this case, because we're doing term-by-term differentiation. And for people who just joined, we're doing part C right now. It is not related to part A or B, so you are fine. I will review the solution in 1 minute. Nice. Time is up, and let's take a look at the solution. So the general term is differentiating the general term. So I will put the n in front and subtract the x1 and 1. Everything else stay the same because they're constants. And for differentiation, we keep the constant at step. You can simplify a bit if you want. And the radius of convergence stay the same after term-by-term differentiation integration, so it is also 6. So you don't need to do a separate test anymore. If you did it, then that's fine. You just verified it. One point for general term, 1 point for radius. Any mathematical expression equivalent to this expression earns the first point. You do not need to simplify, but any present simplification must be correct in order to earn the first point. So there is no point in simplifying on the AP test. The second point is earned only for a supporting answer of 6. You can earn it without the first. There are 2 alternating solutions. So the first one is ratio test. The second one is root test, which is not on the curriculum, but you can use it. To get a point for radius, we just stating that it is 6 because the radius convergence of f is also 6. That earns the point. You do not need to do the ratio test, but if you do, it is also correct. So conversion and getting them correct. If you did use a ratio test, you can take a look. It's also helpful because you might see an FAQ that tells you to get the interval. Yes, if the interval of the radius is also 6, the behavior at the endpoints might change, but the radius will stay the same. We have a question: if the result of ratio test is infinity, what's the radius of convergence and the interval? So if you mean that the ratio is infinity, doing, let's say this is infinity, then yes, the radius is going to be infinity, and there's no endpoints. So the interval is all real numbers. If you get infinity as a result of your ratio, that's going to be interesting because it is always bigger. I don't think that will appear though, because the power series is at least convergent at the center. So it will be at least one case. Let's take a look at the last part D. We're given a gx, a new function. So it is n plus 1 x power of 2n now. N squared is 3 to the power of n. Use a ratio test to determine the radius of convergence of the Maclaurin series for G. So finally, it's time to use the ratio test. I'll be happy to see your answer in the chat. And for this question gives you a hint to use ratio test. And even if a question doesn't hint you like that, you should still use it because we have x to the power of 2n and 3 to the power of n, which are perfect indicators of the usage of ratio test. And we generally use it to determine the radius of convergence anyways. 2n is interesting and it is easy to make some sort of mistake. We'll see later. Careful with this. And if you just joined, we're attempting part D right now. So it is unrelated to previous parts. So we want to use a ratio test to determine the radius of convergence of the Maclaurin series for G, which is given in part D. We only need the radius. And feel free to send your answer in chat after you're done. That'll give me an idea of whether I should keep waiting or go over the solution. Let's take a look. I think I have seen multiple correct answer checks, so I think it's a good opportunity to go ahead. Let's take a look at part D then. Radius of convergence. And we need to take a look at the ratio first. So it is in the form of an plus 1 over an. And remember the absolute value sign. So an plus 1 means the substitution of n equals n plus 1 into this general term. So n plus 1 becomes n plus 2. 2n becomes 2n plus 1 because it's a substitution, which equals to 2n plus 2. The plus sign is too big. And n changes into n plus 1 for both of them. And an stays the same, so we copy paste. I can simplify this using some algebra and take the limit. The limit is the absolute value of x squared over 3, which I don't think you need absolute value because it is always a negative. So for ratio test, we must have it smaller than 1. That's a condition for convergence in a ratio test. And after simplification, I get the absolute of it, as the absolute of x is smaller than square root of 3. So this is radius of convergence. If the question asks you for the interval in the radius, I will test the endpoints, square root of 3 and negative square root of 3 and square root of 3. I will test the endpoints to check whether they're convergent 0 or not, if we're asking for the interval. But since this one only asks for radius, we don't need to do that. That's a fearful. The absolute of x might cancel this border. So it doesn't even need the space. Anyways. Let's take a look at the scoring notes. And for general scoring, 1 point for ratio, if you set up the ratio like this, 1 point if you get a limit, and 1 point for radius. So the first point is earned by presenting a correct ratio with or without absolute values. And the error in simplification will not result in you losing the first point, but it will let you not earn the second point, unfortunately. So usually if you simplify wrong, you will get some point off. The first point is earned for ratios mathematically equivalent to any of the following, because they're equivalent anyways. So we just present a ratio, then you get the first point. The reciprocal ratios will also earn a point if you do an over n plus 1 instead. If you include the reciprocal ratios, you can earn a second point for using limit notation to correctly find the limit of the absolute value. And some responses earn the third point only for final answer of square root 3 with a valid explanation. for using the reciprocal of 1 over square root 3. So it is possible to earn all points if you use the reciprocal, but you need to do some extra explanation. To earn a second point, you also must use a ratio and correctly evaluate the limit of the ratio using correct limit notation. And the third point is earned only for an answer of square root 3 with supporting work. So you have to answer correctly, and then you need to show this step. So some supporting work. So that's all for this FRQ. And I think you all did pretty well in this FRQ. So congratulations. Over the exam for Q3, but it has a classic ratio test to find your interval. This is pretty classic and also error bound. Also, the derivative and final value. So there are some interesting FRQ if you want to take a look later. But we have reached the 2 hour mark, so I have to leave it there. I already have the solutions on the back, so you can do it and then take a look at the solution and scoring out. And here are some resources and tools used. So of course I need to take a look at the course exam description for see which topics are covered. And most of the definition come from OpenStax textbook. I provide a link in slideshow. And Khan is also pretty nice. I use some actual exam FRQs in here. Overleaf is for compounding all the latex present in slideshow. I also use a calculator to double check some of the units. And for more resources, I provided the slideshow link course, 5 and post online notes. AP Classroom, if you are taking the AP exam, you will at least get some daily videos. And if you are taking the actual class, you'll get more resources from your teacher. And also some crack AP kinds of basic questions. They're all in the slideshow if you want to take a look. And we have reached the end of the session. Please take a few minutes to fill out the survey. And I have pasted the survey link in the chat. And your feedback is greatly appreciated. It will help us improve our lectures to help you in the next AP exam. For Calculus BC, the next AP exam is on May 12th. About 8 days away. And please fill out the lecture feedback form. That would be very appreciated. And I do have 2 more calculus lectures next week on Saturday and Sunday. One is final review and one is some office hour where you can ask questions one day before the AP exam. There will be another session next week. So there are 2 sessions, one for a final review and one for questions. And thank you all for joining the session and answering the questions. And see you next time. And please fill out the lecture feedback form. I would love to see more resources so I can adapt my lecture to your needs better. And if you finish the lecture feedback form, you're free to leave now. And again, thank you all for joining. And if you have any questions, you are free to ask now. If you have no questions, I'm going to end the recording. I wait for 1 minute for questions. Any questions, please also still fill out the lecture feedback form. I believe approximately 1 minute has passed, so I'm going to end the recording now. You'll be able to access the recording on YouTube later after the other faculty members upload it.